Today we're going to be looking at Chapter 15, Vapor Power Systems. Have you ever thought about where electricity comes from? The lights are on, your computer's running. What generates the electricity? And almost all the electricity is generated by systems that use vapor power systems. And so the electrical power generation is at power plants that you may have seen. But what happens is they use fuel. So they use fuel, and they're going to use, we'll see, a steam system that this works with. So they'll use fuel, and the fuel can come from a variety of sources: coal, nuclear. A great deal of the power generated is with coal. In the United States, less so, and it's switching to natural gas. I think about 20% is from nuclear power. In India and China, a much greater percentage is from coal. And in China, they're developing nuclear power more than any other nation. And we have gas and biomass. So biomass can be typically trees, but it can be other things. And the advances in nuclear power now are really in ships, submarines. If you think about a submarine, how does it stay under the water for 90 days? It has to have nuclear power, so it doesn't come up. So it can travel underwater. And on large ships as well, aircraft carriers have nuclear power plants. So, submarines, let's say large ships. And what this means is they don't need to stop for refueling, so they have the fuel potential to keep going. And what we want to do is to be able to look at what a system is. And as we looked at gas turbine systems, internal combustion engines, let's look at the ideal cycle that we have for this vapor power one. And this is called the Rankine cycle. And we're going to go through this and modify it and make it more complicated and everything else, of course. But it starts with a steam generator. Or a boiler. So basically it's a steam generator, generates steam, goes into a turbine. So I'm going to have my power come out of here. And of course I have to get the steam back. So I have steam, it goes through and expands, it's still steam. I need to condense it in a condenser and then pump it back. So it goes into a condenser. And now it's a liquid, so I can use a pump to pump it back. And so we have something we call this state 1, state 2, state 3, and state 4. And so let's look at a TS diagram of this. And with the TS diagram, there are certain assumptions that are built into the Rankine cycle, so we'll see what those are as well. And so if I look at the TS diagram, so we have the TS diagram for a pure substance. So steam enters the turbine typically as a superheated vapor. It expands isentropically in the ideal cycle to state 3. And then we're going to condense at constant pressure to state 4. And state 4 is a saturated liquid. And then we compress isentropically to state 1. in the pump, and then we have the heat added. So the heat is added from 1 to 2. We have the heat rejected from 3 to 4. We have the turbine work from 2 to 3, and we have the pump work from 4 to 1. And what we built into this is for any cycle, we have that sum Q is equal to W net, or with the power produced. And this cycle is P equals C, heating and cooling. S equals C, expansion and compression. And we're saying that state 4 is a saturated liquid. So we have these states, and we'll be able to look up what they are, and we'll do an example in just a little bit showing that. And now let me just pull out the heat, the two heat things, so we can see what they are. So from 1 to 2, it's heat in, and as we recall on a TS diagram, the area under the curve is heat. And so then this represents Q in. And then we'll do it, the other one for this represents heat out. So we have those, and then since it's sum Q, this represents W net. So the enclosed area, as we have on all cycles, represents W net, the sum Q. Typically, T2 is about 1100 degrees Fahrenheit, 600 degrees Celsius. And this has to do with metallurgical limits of the tubes. So we'll get into how the steam generator works, but these are metallurgical limits. And so there's a wider range of pressures. So the pressures, of course, affect the material properties as well, but there's a much wider range of pressure. And now let's look at an example. And what I'll do is I'll take this ideal cycle and put in some numbers, and you see basically how we go around it, find the enthalpies, etc., find the network and the cycle efficiency. So I'll leave this TS diagram. So and in this section, developing your skills at looking up the enthalpies in the steam tables is worthwhile. So let's say that we have the P2 is equal to 5 MPa. T2 is 500 degrees C. P3 is equal to 10 kPa. And so now what we're going to do is look up the enthalpies in the steam table. So this is at state 2, it's superheated. So we look up the enthalpy, H2 is equal to 3434.4 kilojoules per kilogram. S2 is equal to 6.9743. And now we look at the process from 2 to 3, is S equals C. And I know that P3 is equal to 10 kPa. And this is going to, in this case, this is in the mixture region. Often it is in the mixture region. So you'll have to find the quality, and then knowing the quality, find the enthalpy. So I'll do that out. So because of the entropy, we have that S3 is equal to 6.9743 is equal to S sub F, 0.64708 plus X3 times S sub FG, 7.5028. So this is S sub F, S sub FG. So you know that then what we do is I'm going to find H3 is equal to H sub F 191.82 plus X3 times H sub Fg, and H sub Fg is 2393. So X3, when I solve for X3 here, it's equal to 0.843. And so now, if we solve for H3, H3 is equal to 2209.9. H4 is equal to H sub F at P4. So this is equal to 191.82. And now what I want to do is I want to go through and do a first law analysis of this. And in the process, we'll find H1. Maybe I'll find H1 right now. And so let's find H1. And so I know H1 is equal to S1 is equal to S4. So now we're going to go through a slightly different process in terms of looking this up, because we're using the compressed, we could use the compressed liquid tables. It's very complicated, but there's an easy way to do this. So let's look at the easy way to do this. So this, if I look at H is equal to U plus PV, DH is equal to DU plus PdV plus VdP. So if I take the derivative, I do that, notice that this is del Q, and del Q is equal to TdS, and the process 4 to 1 is S equals C. So this is 0, so DH is equal to VdP. So H1 is equal to H4 plus the integral of VdP. And we're assuming that this is incompressible. So this is equal to V4 times delta P. And with that, if I substitute in, I have that H1 is equal to 191.82 plus 0.00101 times 5,000 minus 10. And that's equal to 196.86. So you're going to be using this method to find state 1, which is the discharge from the pump. So we're going to be doing that all the time. So you have the Rankine diagram drawn. I got the Rankine cycle with the steam generator and turbine and condenser. You have that drawn, you have that in your notes. And so this is how, whenever we have a pump, we're going to be using this method to find it. And now what we want to do is we want to go through, and in fact, I'll draw a little simple cycle, go through and find each of these points. We found the points. I want to go through and do a first law analysis for each one. So we have 2, 3, 4, 1. And so you have this in your notes. I just drew it again, so I'd have it here to refer to. So let's do a first law on the turbine. So we have Q plus H2 is equal to W plus H3. So we have that. The process is reversible adiabatic. We get rid of that. And so WT is equal to H2 minus H3. And if I substitute, put in the numbers, 3434.4 minus 2209.9. So I have that WT is equal to 1224.5 kilojoules per kilogram. So for each kilogram that flows through here, this is the work that's extracted. And now we'll keep doing this. We'll do it for the pump. We'll do it for the condenser. And so for the pump, we have Q plus H4 is equal to WP plus H1. And so Q is 0 again. WP is equal to H4 minus H1. Let me see. So I have then that this is equal to, I have to find my notes, okay, 504 kilojoules per kilogram. I have sometimes trouble following my notes, as you can tell. And then the net work is the sum of the two. W net is equal to the sum of the W's. So I end up with W net is equal to 1224.5 minus 5.04. So I end up with W net is equal to 1219.46. So that's the net work. We're assuming some of the turbine work that's used to do the pump work. And then let's find the heat in. So Q in is equal to, I'll do this the long way, excuse me. So let's do the first law on the steam generator. So I have Q plus H1 is equal to W plus H2. There's no work done in the steam generator. All there is heat going on. So there's no work done. So Q is equal to H2 minus H1 is equal to 34.4 minus 196.86 is equal to 3237.54. So that gives us the heat in. So of this heat in, it got converted into work, and the rest is heat out. So the thermal efficiency is W net over Q in is equal to 1219.46 divided by 3237.54. 0.54 is equal to 0.377. So 37.7% of the heat in got converted into work. We could find the heat out by simply subtracting these two, and then we'd get the heat out from our sum Q is equal to W net, or first law in the condenser, we have Q plus H3, so the enthalpy of the steam going in is equal to W plus H4. Again, there's no work being done, it's simply a heat exchanger, so I have the Q out is equal to H4 minus H3, which is equal to minus 2018.08. When we get down to the hundredths level, it's a little too much. And I could get the same thing if I did sum Q. So if I did Q in minus W net, I'd get Q out. And if we go back and look at a circle, a pie chart, not a pie chart really, but I do the circle and this represents Q in. So if this represented Q in, about a third was W net, and the rest was Q out. So that's what happened. That's our basic cycle. And now what happens? So normally what we do is we do the work per unit mass. So we do all this stuff here per unit mass, and then we take correction if we want to put in a certain power level, etc. So we do it per unit mass, and then we change that. So now some extensions that we can add to this that are always typically part of a problem statement. So in this case, an extension might be, what is the power produced? What if I want this to produce 500 megawatts? So we're going to say that W dot net is 500 megawatts. With that, I can find the mass flow rate required. So let's say I know M dot S times W net is equal to large W net is equal to 500,000 kilowatts. So we end up, we're going to be in kilowatts, kilograms per second, etc. So now we have M dot S is equal to this 500,000 divided by W net, which is 1219.46, is going to be 410.02 kilograms per second. I don't truly care about the O2, but anyway, this gives us the mass flow rate for the system.